All right, we're here for the last set of notes for the atom chapter, and we're going to actually look at a little bit of math having to do with half-life. So yesterday we talked about what half-life is, and that has to do with radioactive decay. And today we're going to look at how can we actually use the math of it. So this is the first time that you're going to be kind of mathematically challenged. So if we get started. So first thing, remember we said that a lot of isotopes occur naturally, that being an isotope is completely natural, but what we're going to look at that are some other ones that are synthetic, and we do have the ability to actually look at things that we make and then let them break down. Radioactive decay we talked about yesterday, but it is a first order kinetic process. What that means is that it always takes the same amount of time. So it's not like one time uranium is going to take 5,000 years and the next time is going to take 25,000 years. All that first order kinetic process means is that the time remains constant. And when we have this time, we call it a half-life. And basically, it's how long it takes for half of it to break down into something new. It doesn't disappear. It doesn't, vanish from the face of the Earth. It just changes into a different element through a nuclear reaction. So if you look at the bottom there, we have at the very beginning blue dots, 10 blue dots, and they are all radioactive. And then if they're saying that's carbon-14. And what happens is, on the right, if we would come back and look at it about 5,730 years later, about half of it, 5 of those dots, have now turned into a new element. And we call them the daughter atoms because they're no longer the same. They came from the parent, but they're different, so they're the daughter. And that amount of time is our half-life. All right, so right here we have strontium-90 has a half-life of 28.8 years. We want to know how much is left after 115 years. Now this is like a very simple, just middle school thing. We're just going to show you kind of what, anytime you have a half-life, what the decay looks like. So what we're going to do is, first we're going to have to make an assumption, and we're going to assume that we're going to start with 10 grams. So they didn't tell us that, but we're just going to assume that to kind of help us through. And what they're saying is we're going to let it sit for 115 years, and every half-life is 28.8 years. So we want to find out how many half-lives does it undergo, because it's not just like one half-life and you're done. So what I'm going to do is take how long, 115.2 years, and divide it by how long each half-life is, 28.8 years. And it turns out we're going to let it sit there for 4 half-lives. And this is, again, kind of a middle school one because everything works out perfectly. We usually don't let things sit for exactly 4 half-lives, 5 half-lives. But we're just looking at it right now. So if we use our graph over here and we say this is our half-lives and this is our amount, at the beginning, we're going to say that's time 0, so 0 half-lives. We said we're going to start with 10 grams. And now we're going to have 4 half-lives, so I'm just going to number down 1, 2, 3, and 4. And what we're going to do is just say, okay, what happens as we go through? So after 1 half-life, if we start with 10 grams of the strontium-90, now we're going to have 5 grams. If we let it sit for another half-life, we're going to have 2.5 grams. If we still let it sit for one more half-life, we get 1.25 grams. And at the very end, after 4 half-lives, we are only going to have 0.625 grams of this guy left. So you can see that pretty rapidly we're losing a lot of our amount. And you always have this where at the top, you're going to lose the largest amount at the top. And as we go down, we're going to lose less and less because there's just not as much to lose. And we're just going to really simply graph it, nothing big or beautiful or anything, just kind of simply looking at it. And just to show you what it would look like. So it's a graph, so I'm going to label it. So I'm going to call it strontium-90 decay. I'm going to put my time. Let me have a little more room here. I'm going to put my time in years on the bottom. I'm going to put my mass in grams on my y-axis, and you will need to have those, always need to have those. And for my time axis on the bottom, I'm going to go by 20s. So 0, 20, 40, 60, 80, 100, and 120. And for my max, up my y-axis, I'm going to go by 2s. So 0s at the bottom, we're going to have 2, 4, 6, 8, 10, and 12. And then we're just going to graph it. So if you look back on your chart, at half-life 0 times 0, we had exactly 10 grams. So we're going to put a dot right here, 0, 10 grams. Then you look and say, okay, after one half-life, it's about 28.8 years, about 30 years, we have 5 grams left. So you go up to about 30 years, and you make a dot right there. And you just keep going. So we're at almost about 60 years for our second half-life, and we're down to 2.5 grams. And again, this is just rough. Keep going. We're a little above 80, and we have 1.25. And then way out past 100, we're already down. And what you're going to get, again, a rough graph, but you get this decay graph that every single thing that has a half-life is going to follow, this decay graph. And again, it's just to show you what it looks like. Okay, so what we're going to do is just talk about some of the different types, really quickly review like how it works, and then we're going to do 2 problems with half-life. All right, this next chart, you don't have to write them all down. Again, if you want this, you can print it out from Moodle. You can look it up on Moodle. What you just want to look at is there's 2 categories. There's the natural isotopes up on the top, and you have the synthetic ones. And if you notice, the natural ones tend to have longer half-lives. Tend to. Now, carbon-14 is a pretty short one. But it's just that if you're natural, you tend to be a little more stable, even though you are radioactive. The synthetic ones, if you look at iodine, is like ridiculously fast. So it just means it tends towards natural half-lives have or natural radioactive isotopes have longer half-lives. Synthetic ones have shorter ones. There's not really a trend on what type of decay, alpha or beta or anything like that. That's just kind of inherent to the actual isotope. So keep that in mind. All right, and then last thing, then before we take a break, and then we'll do our calculations, is we're going to use it for dating. That's what the biggest thing that we use it for. And remember, the reason we do this is because any nuclide, and remember, a nuclide is just a specific isotope, is constant. So we actually use it as a clock. And when we're looking at organic things, 95% of the time we're looking at carbon-14. And we went over this yesterday, but just to kind of go through it again, remember there's a ratio of carbon-14 to carbon-12, and it's been the same on the Earth for about 50,000 years. And we keep getting this carbon-14 because the plants photosynthesize, and when they photosynthesize, some of that carbon is carbon-14. We eat that carbon-14, and it becomes a part of us. And then as long as we're alive, we have that ratio, that constant ratio. And when we die, unfortunately, we no longer replenish it, and the ratio starts to decrease. And we use that ratio to figure out basically how old we are, how long ago we died. Again, we said yesterday you can't use carbon-14 for things that weren't alive, so we can't use it for rocks. And you can see we use uranium-238 for rocks, and it's pretty useful because you can see the half-life of uranium is much, much longer, so we can date rocks that are much, much older. So again, what we're going to do is take a little break, and then you're going to do the actual calculations. The calculations have to do with some natural logs. You're going to need a calculator with it. And we're looking at things that aren't, you may have done half-lives in middle school, but this is an actual kind of real half-life. What happens when, what would a scientist actually use?